Good morning, everyone, and welcome back to Project CD Chronicles, or welcome. If it's your first time with today's video, we will present a new challenge, particularly with our beloved Commodore. 64 can also be used for Commodore 128 in 64 mode. And we will ask ourselves, can the Commodore, through BASIC, simulate what is an associative neural network like that of Chat, GPT, or others, a small experiment through a basic program. Stay with me until the end of the video because we will tackle the various aspects and then delve into it a little. How the basic program was constructed. Well, now before proceeding, we have our program in front of us. By the way, a part of these executions will be put in Word because clearly basic is rather slow. We will first aim to teach what is a brain, some letters of what are the COM64 through the ROM characters in particular, initially using patterns and then causing variations. Now let's first look at the matrix that can likely be identified as the brain. This is in warp mode. You see that as a matrix, everything is exactly at 0. That is, it has no information and is not able to recognize anything. So what we aim to do is through reading the ROM, the characters, which in this case it reads basically, with F1, we do a teach pattern, and then it begins a whole training phase. At this point, let's say it has started to, so to speak, memorize and learn what the letter is. And as you can see, the character matrix itself has likely started to change its appearance because we have to think that each of these small cells is a neuron, and each of these small cells is interconnected with each other, of course. And so we have a 6-7 character matrix with a more extensive 42x42 matrix. 42 by 42. Now, however, let's proceed to conduct a second experiment. We fetch what is the B, which it reads correctly from the character ROM, and we have the teach pattern. In this case, we always put it in WAR because it's a bit slower, and for YouTube timing, it would be very high. We have an dump of what is the character matrix, and as you can see, the matrix itself has started to change exactly what they are, and pay attention. I'm already starting to introduce it. Thank you. The various weights, more or less, through the connection of the various neurons. This is because the matrix is starting to learn. Learning in itself what the recognition of the various provided patterns there is. Well, let's go and see some more detailed information. Well, before proceeding, let's return to the author's page and go back to 1987 by John Walker. As he says, this was my boldest venture into programming the Commodore 64. It is a complete recognizer of associative patterns and memory based on neural networks implemented, and we will see it in less than 250 lines of CBM64 basic, and it is possible to train the network on a variety, so to speak, of letter and number patterns, and then recognize those that are similar patterns. Then he, continues by saying that he submitted it to a series of Commodore magazines, each of which rejected it as too esoteric. I prefer to consider it simply a literal process. And this is what the author says. It must be said, and we will see it shortly anyway, that these patterns, so to speak, have their historical origins in what are McCulloch and Pitts and the Perceptron. They were developed anyway in the 70s, 80s, and 90s. What is the simple reason that only in our days has it been possible to see the realization of these neural networks? For the simple fact that they need an enormous amount of data to be trained and a significant computational power. Let's imagine that. Here it is about some letters, but now we, faces, characteristics, language, and so on can be recognized. We must nevertheless trace back to the perceptron, which is one of the first simple neural networks, McCulloch and Pitts, as I was telling you. And essentially, we could define it as the sea anemone, an input neuron, an internal neuron that are defined as layers, and an output neuron. So the first gives me a recognition pattern. The second is what functions so that it can be trained and recognized. And then an outcome that can be, in this case, depending on whether I set it to a BC or numbers. So the input pattern, the function, and here we have the internal neural network with the various interconnections of neurons as we saw here in the Commodore 64. And then it gives us an outcome that can be 1, 2, 3, 4. In reality, here we are talking about numbers, so to speak, floating point numbers. So lightning, they have a variation from 1 to 0.7 to 0.5, thus a much smaller variation. Anyway, essentially, beyond what the input pattern is, it still gives me, so to speak, an output number that identifies the pattern model. Now, pay attention because I have selected here Perceptron. And remember what this formula is, the scene. Clearly, these are very, very simple networks. Nowadays, we consider them as stupid. In this case, they are feed-forward networks, as the word suggests. But what interests us is remembering what backpropagation is. So in this case, for example, we have a pattern that we can see from the Commodore 64, which is here the B, okay? And this is the pattern. And I am telling it that this B, practically to identify that it is a B within this matrix, goes to identify some dots as on and off. Well, in this case, we have this input. And I also tell it through this second piece of information here that this pattern actually corresponds to the B, so that when I then type the B, it will technically recognize this pattern with variations and approximations. Now, what happens here, and why is the word training used? Because clearly it can happen that in artificial neural networks, there are errors and they need to be trained. That is to say, if I put C, a pattern, yeah, here and actually here, I tell it to press B, clearly it might give me an incorrect result. So here we have this backpropagation, retropropagation, and here it is implemented well regarding a basic on these types of functions, where it calculates a whole series of values backwards so that the network can self-correct. Clearly, this type of learning is called supervised learning because I have exactly the input pattern that I need to tell it to recognize, even with variations. As you can see here, it starts to make variations to recognize this. But I also have the same letter, B, that I pressed. And so in this case, I can do a training on this small variation. So I am telling you that the letter, not only is it the same as what the character ROM is, but it could also undergo some variations. This is simply because cursive writing is in fact different from the other. And here too, as you can see, the network started to change simply with a single pattern that initially changed. So technically, if I have a CR and also my B is not written well, or does it have minimal variations? Here practically, the COM104, like another GAR, will be able to recognize this type of learning more or less correctly, this type of letter. And here we talk about backpropagation. Now we need to get back to us. What are brains made of inside? Clearly, in our brain, there are neurons. Here there are axons. Thank you. And here are the various dendrites. Clearly, each neuron is connected to others. And thus, we can define billions of neurons for billions and billions of connections to other neurons. And essentially, these neural networks, as they are presented, tend to simulate what is the very nature of our neuron. And ultimately, we have the output of a session. So imagine that the electrical impulses enter here. At a certain point, the neuron reaches what is an excitation threshold, and thus it is dictated by these functions. And when it reaches a certain threshold, and this, for example, let's say it's 0.5 for the letter A, but let's say it's 0.6 for the letter B. Here it sends out a specific signal, thank you. And this is how we have all the various connections of our neural network, just as it happens in the dump of what is the neural network of the Commodore 64. Here you have to think that each single cell is connected to others. Clearly here it is very, very simplified, precisely to respect, let's say, this type of conformation. And so we will have the input pattern, which are the dendrites. Our neural network, which is the dump, and we will have a number that will identify exactly what the output session is. Well, let's return to our article, but I'll leave the in-depth exploration to you because I'll provide the link. Essentially, we can say that the remarkable thing about this program is that it doesn't know how to recognize letters and numbers. As for the program, it could even learn sentences, musical phrases, combinations of medical symptoms or animal images, because essentially that is what the input is, that is what the internal neural network is, that is what the output is that we will take into consideration. So how is the implementation of this program carried out? The program essentially simulates two fields of neurons with F for 101, 1, which we will call F1 and F2. And these are the matrices, as I mentioned here, F1 and F2 are these here. And it displays them in the two windows on the screen. When a letter or a number is typed, the pattern corresponding to that symbol is initially read from the character ROM and then stored in F1. And the points are illuminated as if it were more or less a character, so 1 and -1. So we turn them on and off. And it is placed in what are initial patterns of 6 by 7, which are F1 and F2, which contain exactly 42 numbers. And then we will see that the matrix is formed by 42 by 42, but we will look at them directly now in the basic program. This is the basic program, as I was telling you, and I have slightly modified it. We have an initial dimension of what are the initial patterns, the final pattern, the pattern with variations, and what is the matrix itself. And here, as you can see, we have 6 by 742, and it takes what is the 8 by 8 character ROM. Clearly, there is a routine that then retrieves it, but this is simply to retrieve the characters, nothing special. The program continues with the teaching of the pattern, showing the matrix. We can also forget everything and do a recognition. And then even once this program learns, we can save it to disk and reload it to get our new configuration. Well, let's always return to our page. So we can say that each neuron EK in one field potentially connects to every other neuron in another field. And thus each connection is equivalent, as I showed you earlier, to a synapse in the brain. And each synapse has its own weight. And so if we go here to dump the matrix, these small numbers identify the weight that the matrix itself has. It is clear that if it were a floating point number, it would be more accurate. And this happens precisely to excite the neuron itself in a positive or negative sense. These weights then, as you can see here, are stored in what is the matrix. 42, 42, 42x, 42x, 42. And so we have a total of almost over 2,000 connections. All right, now, a particular number is mentioned in the paper I showed you. And what happens in this case? So let's look at it in more detail. To learn, and so we have the learning process, a pattern. We provide a matrix, as I told you before, starting from what is the initial pattern F1, which is always this, and we add it to what is the matrix. And now we are going to look at them in what are rows 1020 and 1060 that I had seen here before. So essentially, in these lines, to learn a pattern, we form a matrix, starting from the pattern F1, and we add it to the weight matrix M. And here we have the lines. To recall a pattern instead, we need to go to this line. Okay? Be careful, because here it is quite complex, because we have to go from F1, which is our initial pattern, and should we convert, we will need to retrieve it from the entire matrix and essentially obtain those patterns which are either 1 or -1 or 0 to leave unchanged. Once I have obtained this, it will clearly be able to reconstruct. From our initial pattern to the matrix, we go back to the exact configurations of on or off. From the initial pattern, it moves from F1 to the matrix, constructs F2, and compares them. And then it is able essentially to achieve a more or less correct effect, even though nowadays they are no longer applied, or rather, they are actually from internal neural networks to internal neural networks to internal neural networks, because now there are transformers. Anyway, essentially this was the application made. On the Commodore 64 too, managed to simulate what is a perceptron, precisely a model of an artificial neural network, the first of its kind introduced by, as I was telling you, McCullough and Pitts. Well, to finish, we also did the B. We can do what is a recall pattern. You see that it first goes through the neural network and then from the letter F2 does the inverse part and goes to recognize what the pattern is through the parts we have inserted. And here, then we can later go on to play a little more as we like. So here I have made numerous variations of what the letter A is, as you can see in this example, and what our pattern is, which is a ROM of characters. Now it is able to recognize a greater conformation, even if it is perhaps poorly written. Anyway, not well. And our internal pattern has undergone a conformation that is different. And indeed, by pressing the A, it recognizes that it is indeed an A, but from a pattern that is modified compared to the original. Well, what can I say? Let's return to conclude with our original article. John Walker, September 1987, September 4th. We thank for having delivered to us today this gem that has allowed us to take a dive into the past and a step forward in what is our present and future, also to be able to understand how our current artificial neural networks are actually made. What can I say? I thank you for coming this far with me. I wish you a good continuation, and we'll see each other soon on Project CD Chronicle. Thank you all, Claudio.